Okay, now we're going to cover Chapter 4, and the title of Chapter 4 is Reactions in Aqueous Solutions. Now, as we talked about before, aqueous means that water's the solvent. There'll be solutes dissolved in water, so that's called an aqueous solution. And these are important in chemistry and also biology, because in our body fluids, we have aqueous solutions with dissolved solutes. So we learned what a solution was in previous chapter, and a solution is a homogeneous mixture. It has one phase throughout, same properties throughout the mixture, and to have a solution, it's a mixture of two or more pure substances. And whenever there's a solution, you have to define the solvent versus solutes. You can either have one solute or many solutes. And the solvent is the one that's present in the greatest abundance. So in aqueous solutions, we're saying that water is present in the greatest abundance, and so water is a solvent in most of the problems and discussion in this chapter. But water doesn't have to be the solvent. For example, if I had a 40% ethanol solution, then water is a solvent. It'd be 60% water and 40% ethanol. But if I had a 95% ethanol solution, there it's only 5% water and 95% ethanol. So in that case, ethanol would be the solvent. But like I said, in this chapter, we'll mostly talk about water as a solvent. So water solutions are aqueous solutions. Here's an example of a solution of methanol in water. So here we have our Mickey Mouse water molecules, the two hydrogens and the oxygen that we'll talk more about in a minute. Then here you have your methanol molecules, which is an alcohol. Got your carbon, oxygen, and hydrogen, CH3OH. This is the group that makes it an alcohol, the OH. And if it's an alcohol, the OH is attached to a carbon. So this is the simplest alcohol called methanol. And met means one carbon. It's really organic nomenclature, not inorganic, but met means one carbon. And the all means alcohol, OH. So on the molecular scale, this would be a methanol solution where water is a solvent. You can see there's more water molecules present than methanol. So here water is a solvent, and methanol is dissolved in the water, so it'd be a solute. So here we have one solute with the solvent. So all other substances in our solution are called solutes. And here there's one solute, methanol. Okay, this is a famous slide. Like dissolves like. And what I mean by that, if there are no charges present in a substance, it's called hydrophobic or nonpolar. And so a nonpolar or hydrophobic substance, and the greatest example is when you just have all carbons and hydrogens in your compound. They want to be around other nonpolar hydrophobic substances, and so they'll dissolve in each other. And so water is actually a partially charged species, I'll talk about in a minute. Even though it's a molecule, and they say it's neutral, it has partial charges. And so we're not going to learn about the partial charges that much until Chapter 8, but we have to discuss them a little bit here so that we can explain how water can dissolve a salt, some salts. And so since water is a partially charged molecule, it actually has very strong partial charges, it can dissolve anything with charges or partial charges. So that's why it's a universal solvent, because of those strong partial solvents, charges. And so this is an example. We've looked at this before. This is a sodium chloride crystal. You have your chloride ions, the big green spheres, and the purple-gray spheres are sodium ions, Na+. So we learned in a salt crystal, it consists of ions with charges, but the total charge on the crystal is neutral. And so here we put a salt crystal in water, and the water is going to start to dissolve the crystal. And you'll notice, this is our Mickey Mouse water molecule. The two hydrogens have partial positive charges, okay? And the oxygen has a partial negative charge. And opposite charges attract, so you'll notice the way that a chloride ion is pulled out of the crystal, it has to be hydrated by water molecules. This is called hydration. And this is what aqueous means. When we put Cl negative aqueous, it means it's in solution surrounded by water molecules, held in solution because it's bonded to the waters of hydration. And you'll notice, since this is negatively charged, the partial positive charges of hydrogen are attracted to it. And so this is actually three-dimensional, and when the attraction to the water is greater than the attraction to the crystal, it will solvate it and it will dissociate it and pull it out. So this is how ions dissolve in water. And you'll notice with sodium, it's positively charged, and the partial negative oxygens surround the positively charged sodium ion. And you'll notice the sodium is smaller, so you can fit more water molecules around the sodium. And once again, water will go ahead and surround sodium, and when the attraction of the water molecules is greater than the attraction of the crystal, it will solvate it and pull it out of the crystal. And now these are soluble. See, these are aqueous now, Na plus aqueous, a Cl negative aqueous. So that's what aqueous means. It's solvated with water, keeping it in solution. And so when an ionic substance dissolves in water, the solvent pulls the individual ions from the crystal and solvates them. And it solvates them with this opposite attraction of the polar water molecule. Remember the partial negative oxygens in the water, one of them, and the partial positive hydrogens. And this process of solvation is called dissociation. When a salt crystal dissolves into ions in solution, is called dissociation. So let me draw some of this on the board and show you the partial charges. Okay, so you'll notice every time I've drawn a water molecule, I've drawn it bent-shaped. That's why I call it Mickey Mouse, because it's kind of like Mickey Mouse ears. The angle's almost correct. And so here we have our big oxygen atom, and here are the ears of the hydrogens. Okay? And we'll learn in chapter 8, the hydrogens have a partial positive charge. The Greek letter delta means partial. A full charge would be like 1 plus, 2 plus, 1 negative, 2 negative. But in this case, delta means less than 1, but it's greater than 0 charge. So it's a partial charge. And so the oxygen here would be a partial negative. So there are the partial charges on the different atoms in water. And once again, we'll learn why with electronegativities in chapter 8, where these partial charges come from. So now, let's go ahead and show how a sodium ion is solvated. So here we have a sodium ion, and then so it's going to be the oxygens of water that are attracted to the opposite charge. And there's more, but we'll just draw that many. Remember, these are the hydrogens, the ears, and this is the oxygen. And each oxygen has a partial negative charge. So the partial negative charge on the oxygen is attracted to the positive charge on the sodium ion because opposite charges attract. And so that's how a sodium ion is solvated in water. And chemically, in a balanced equation, we'd represent this like that. See, this shows you that there's water surrounding the sodium ion to keep it in solution, that it's dissolved. Now let's draw a cartoon of how the chloride ion is solvated. So here we have a larger chloride ion, and now the hydrogens surround the chloride to solvate it. Because the hydrogens are partially positive. Okay? And so a chloride ion is solvated with the hydrogens attracted to it to pull it out of the crystal. Okay? And so this one, the magical properties of water, it has these strong partial charges. So therefore, anything with a partial charge or full charges most likely can be soluble in water. They're called hydrophilic. And they like to be around water. See, hydrophilic, water-loving. So this is an important concept to know in biology, because in biology you want to know things that dissolve in water, because most of our, our body fluids are aqueous solutions, and the ones that won't. Okay, and so in a chemical equation, we'd represent the chloride, the solvated chloride like that, chloride aqueous. Okay, let's go back to the PowerPoint. You'll notice here sodium chloride, when it becomes solvated, is called an electrolyte. Let me make sure it's called an electrolyte. Because an electrolyte is a substance that dissociates into ions when dissolved in water. So here you've got a salt crystal, and when it dissociates, you've got negative ions here and positive ions here. Negative, positive. Okay? That's the definition of an electrolyte. A substance that dissociates into ions when dissolved in water. And that's a really important definition we need to be familiar with in the first part of this chapter, because we're going to use it over and over again. And it took a long time for scientists to figure out how electricity was conducted in a liquid solution, because they knew that electrons just didn't flow out in water by themselves. You never get naked electrons. And so they knew it wasn't electrons. And Einstein's actually the one who discovered how an electrical current is conducted in a liquid solution. He said it was the ions, the flow of ions in the solution that conducts electricity. And this isn't a well-known thing that Einstein did, but he's the one that explained how water solution conducts. And so it is ions. So a non-electrolyte, the opposite, it can dissolve in water, but it does not dissociate into ions when it does. It remains the whole molecule without a charge, a neutral molecule. So example, methanol is a non-electrolyte. So we've got CH3OH. And when it dissolves in water, it still remains CH3OH. It does not dissociate into ions. Now we need to differentiate between electrolytes and non-electrolytes. And then within the electrolytes, we need to differentiate between a strong and a weak electrolyte. A strong and a weak electrolyte. And you need to memorize the strong electrolytes, the weak electrolytes, and then the non-electrolytes are all other compounds that aren't strong or weak. But you need to memorize these. You memorize the strongs, and these will make sense when we discuss them, and the non will make sense. So soluble ionic compounds, and remember ionic compounds can be salts or hydroxides, the strong, like sodium hydroxide, lithium hydroxide. They tend to be electrolytes. And so all ionic soluble compounds are strong electrolytes. So they'll have aqueous next to them, like NaCl aqueous, KCl aqueous. But actually all salts, even the insoluble salts, are strong electrolytes. And I'll explain that in a minute. So even if you have a solid next to a salt where it doesn't dissociate 100%, it's still a strong electrolyte. And I'll talk about that in a minute. And then the molecular compounds that are strong electrolytes are strong acids. And there are 7 strong acids in table 4.2 that we'll see in a minute that need to be memorized. Then any other acid will be weak, considered weak. And we learned that the way you differentiate whether a compound's an acid, it has in inorganic chemistry, the acidic protons are first in the formula, like HCl, HI, HC2H3O2, acetic acid. And so any other acid is weak. In any other base, we're going to memorize the strong bases, strong electrolytes. Any other base is weak. And so the weak acids and the weak bases are the weak electrolytes. Okay, you need to know that. Molecular compounds tend to be non-electrolytes except for acids and bases. So here's a molecular compound. Methanol, and it stays together, nothing dissociates. And so it's a molecular non-electrolyte. Okay, this is an apparatus in the lab. You can tell whether or not something's an electrolyte or not. And we have some in the lab, so remind me when we do our titration lab, I'll demonstrate, or even the metathesis lab, I'll demonstrate this apparatus. And what it is, you have an incomplete circuit here. You have 2 electrodes, okay, a plus and a negative hooked up to a light bulb. And you plug the light bulb into an electrical circuit. And then you're going to put it in a solution. And if the solution does not have ions, it means it's a non-electrolyte. For example, this is put in distilled water here. Distilled water, when the distillation process, you get rid of all the ions in the water, dissolve solutes. And so here, this is on, it's plugged in, we put it in pure water. Oh, there's no conductivity of electricity because the light bulb is not lit. So this would be a non-electrolyte. Water, H2O liquid. And with the solvent, in a liquid solvent, if it's a solvent, you put L, the letter L, small letter L. That indicates in a chemical formula that that is the solvent. Now we're going to take some table sugar, which is sucrose, and we're going to mix it into this apparatus. And it still doesn't light when the sucrose dissolves in the water, and that means that sucrose is a non-electrolyte because it does not conduct electricity with our apparatus. So this is how you can tell if something's a non-electrolyte really quick. Dissolve it in water, see if it lights up the light bulb. Now we're going to take some table salt, sodium chloride, and a new solution of water, and we're going to dissolve the sodium chloride in the water, and wow, look at the light bulb. Not only is it lit, it's lit brightly. And so we'd call this not only an electrolyte, it's a strong electrolyte. If the light bulb lights up very brightly, it's called a strong electrolyte with this apparatus. If we put a weak acid in there, like acetic acid, it would still be lit, but very dimly. You could turn out the lights and just barely see the filament on. Definitely weaker glow than strong. And so we call it a weak electrolyte. So with this light bulb, not only can you tell whether something's an electrolyte, you can differentiate whether it's a strong or a weak electrolyte. Okay? So a strong electrolyte dissociates completely when dissolved in water. A weak electrolyte only dissociates partially when dissolved in water. So let me explain that a little further. Okay, solubility and electrolyte strength are not related. Some salts, you learn in Chem 122, they're not very soluble. and when you put them in water, but they all dissolve a little bit. And the part that is solvated dissociates 100% into ions, okay? And so I can put, like, if I remember right, calcium fluoride. Well, let's do let's see. Okay, when you put calcium fluoride in water and stir it, you'll get a little, see, this is solid calcium fluoride. You put it in the beaker, and you'll get a little bit of ions dissociating. So you'll get some fluorides and some calcium ions that'll be solvated, but most of it will stay solid. You go to the bottom of the beaker, and it'll be solid calcium fluoride. This is called an insoluble salt. An insoluble salt. We learned about insoluble salts in Chem 122, and we can actually calculate the amount of ions in solution with the insoluble salt once we study them. But we don't do that here. But the thing is, all salts dissociate a little bit. And that's what these double arrows mean. Once again, we learned the double arrows in Chem 122. That means the reaction doesn't go to completion. It goes this way, and it's going both directions, and then you reach equilibrium conditions. But you're not going to be held accountable for equilibrium in Chem 121, but I have to introduce a little so you'll understand. And so any salt that dissolves in water will produce some ions. And to produce ions, the part that dissolves always dissociates 100% into ions. So that's the definition of electrolyte. The part that dissolves dissociates 100%. So this part that doesn't dissolve, it doesn't dissolve and it's not producing any ions, but the part that does dissolve does produce ions. And so those ions will make it a strong electrolyte, even though it's an insoluble salt. So all salts are strong electrolytes. All salts are strong electrolytes. There's actually 4 exceptions, but your book doesn't mention them, and so we won't talk about them. You won't have to learn the 4 exceptions, okay? The 4 salts that are not strong electrolytes. So any salt is a strong electrolyte as far as we're concerned. Now, the same thing with a weak acid. Let's look at a weak acid and learn why it's not a strong electrolyte. So here we have acetic acid. Okay. This is the famous weak acid when you study acids, acetic. And once, just like that insoluble salt, it dissociates a little bit. Into ions. See, this is the acidic proton. Inorganic chemists put the acidic proton first, and it will pop off and then leave the acetate behind. The acetate, and that's the first polyatomic ion on your common ion table, 1 negative acetate. And once again, though, in solution, it's mostly this. This stays together in the water dissolved. It's aqueous. But a little bit ionizes, so this will conduct electricity. But only a little tiny bit ionizes. The part that's mostly this. And that's why it's called a weak acid. The stronger the acid, the more it ionizes, produce H pluses and ions. Okay? So even with weak acids, there's different strengths of weak acids. And acetic's one of the stronger weak acids. But once again, that's Chem 122. And so you don't have to use the double arrows in here. I'm not going to hold you accountable for it because that's really Chem 122. But that's what the double arrows mean. It only happens partially. But see, since it does produce some ions, it's going to conduct. But it's only going to conduct a little because there's just a little bit of this and a whole lot of this. Okay? Let me show you acetic acid, what it really looks like. This is the structural formula for acetic acid. And this is the acidic proton right here. This is the one that can pop off a little bit. These are not acidic. These are protons, but they're not acidic. This is the acidic proton. And so when it pops off, you get a negative here and a plus here. So you get some acetate. This is C2H3O2 negative. See, C2H3O2 negative. There's a double bond here. And so that's what it looks like. You'll have some acetate ions, and that's a C2H3O2 negative aqueous, and you'll have some H+. This makes it an acid. Anything that dissolves in water and produces H+ is called an acid. Okay? And the inorganic chemists write it like this, where the organic chemists write acetic acid like this. They separate, they show that the acidic proton's on that oxygen. But since this is inorganic, in the book they'll actually have both of these, but we'll stick with the inorganic nomenclature. And if you go to organic chem, they'll write it like this to show it's a weak acid and where it's attached to. Okay. So once again, a strong electrolyte dissociates completely when dissolved in water. The part that dissolves dissociates completely. And a weak electrolyte only dissociates partially when dissolved in water. So a lot of it stays undissociated. Even though it's aqueous, a lot of it stays undissociated. And the famous weak base is ammonia, NH3. So now you know the famous weak base and the famous weak acid. The famous weak acid is acetic acid, which is the acid in vinegar. And then the famous weak base is ammonia, NH3. Okay, you get to memorize this table. Memorize. Okay? These are the strong acids and strong bases. And see, it's not that much to memorize. And then you know the weak, any other acid or base, any other hydroxide, see OH negative here, that's hydroxide, will be a weak base. And any other acid with the H first will be a weak acid. So you don't have to memorize the weak acids, just any one that's not one of these 7. And you can see a pattern here. These are 3 halogen acids. HF is not, put that in your notes, HF is not a strong acid. We'll learn later the bond between the H and F is so strong it's hard for that H to pop off. It's a weak acid. HF, hydrofluoric acid, is weak. But the other halogens, HCl, HBr, HI, are strong acids. And this is the one, the most famous one, hydrochloric acid, is HCl. Okay. And so these are in the same group, 7A, chloride, bromide, iodide, are protonated to give a neutral formula. And see, these are molecules in the gas state. Acids are molecules as gases. It's actually a covalent bond, nonmetals. They're molecules. So in the molecular nomenclature, if this were a gas, this is hydrogen chloride, hydrogen bromide, hydrogen iodide. That's the binary molecular nomenclature we learned. But once they go into water, the hydrogens can pop off, and they increase the hydrogen ion concentration, H+ in solution, then they're acids. And then they're aqueous, so you don't use molecular nomenclature in water, because then they're acids. And the hydro-ic means the anion ended in ide. You look at the anion of the acid, and if it ended in ide, IDE, it's a hydroic acid. And since this is chlorine, it's hydrochloric acid. Oh, and bromide, so hydrobromic acid. Iodide, anion, so hydroiodic acid. And this is in the end, in your book in the end of chapter 2. And then ic acid means that the anion of the acid ends in ate. This is chlorate, so it's chloric acid. This is nitrate, so it's nitric acid. This is sulfate, so it's sulfuric acid. So that's what ic acid means. It means the anion ended in ate. And see, this was the perchlorate ion, so it's perchloric acid to differentiate from chloric. See, chlorate becomes chloric acid. Perchlorate ion becomes perchloric acid. You keep the per so you know you have 4 oxygens instead of 3. So you learn these 3, HCl, HBr, HI, that's a pattern. And then you know these 2. These HCl and these 2 are the most common acids, nitric and sulfuric. This is the battery acid in your car. So now you know it's H2SO4, HNO3. And then these you memorize, but they're right next to each other in oxygens. This is chloric acid, came from chlorate, and this is perchloric. And so you memorize these. If you ever see these are strong electrolytes, because all strong acids are strong electrolytes. Okay? All other acids are weak electrolytes. So let me give you some common weak acids that you see. So let's list some weak acids. I can get this out of the way. Okay, some weak acids. The most famous one is HC2H3O2, and once again that's acetic. And then hydrofluoric. So this is fluoride, so it's hydrofluoric. And this is acetate, so it's ic acid, acetic acid. And the acete means 2 carbons. That's actually organic nomenclature. So they say acetic because acete in organic chemistry means 2 carbons. So it's an acid with 2 carbons, acetic acid. And then HCN is also a very common weak acid. And the anion there, you should know, is cyanide. So since it ends in ide, it's going to be a hydroic acid. So that's hydrocyanic acid. Hydrocyanic acid. Because ide is always hydroic acid. Hydroic acid. And then this is acetic acid because it ends in ate, so it's ic acid. And this one's hydrofluoric. Because the anion ends in ide, so it's a hydroic. So those are 3 of the real common weak acids you'll see sometimes. And another one, I'll put up a weird structure you've never seen before. But the organic chemistry way, whenever you see a COOH, that's a weak acid. Those are the common weak acids in biochemistry and organic. So once in a while, even in Chem 121, you'll see a COOH, and that means it's a weak acid. Okay? No matter what it's attached to. Weak acid. Just remember, we could write acetic acid like that. The organic way, oh, COOH, weak acid. Anything with COOH on it, say, oh, that's a weak acid. And those are the common weak acids in our body with COOHs. Okay, now let's learn some of the strong bases. These are the strong bases. So any alkali metal salt ionic compound of a hydroxide, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, those are strong bases. Okay? And you know this one, sodium hydroxide, is the most common. This is also known as Li. Li. And that's the famous strong base, sodium hydroxide. And then of group 2A cations, only calcium, strontium, and barium hydroxides are strong. You see calcium's here in group 2A, strontium's right under it, and then barium. So we go calcium, strontium, barium. Hydroxides of these group 2A cations are also strong bases. Magnesium hydroxide is above here. It's not a strong base, just these three. So look at the periodic table. Instead of memorizing, look at the pattern. All the alkali hydroxides in that group of three in group 2A going vertically down are strong hydroxides, strong bases. The rest of the hydroxides are weak. For example, iron, 3 hydroxide. Iron 3 hydroxide. Oh, that's a hydroxide, but it's a transition metal hydroxide, so it's weak. Okay, it's a weak base because it's not one of these hydroxides. So once again, you need to memorize this table, table 4.2, the strongs, and the rest are weak. So the weaks are no problem. You got to know the strongs really well. Okay, so let's review. Here are the strong electrolytes. Strong acids, strong bases, and soluble ionic salts. Really all ionic salts. Okay? Strong acids, strong bases, and salts are strong electrolytes. Okay, now we're going to learn one of the most powerful pattern types reactions in all inorganic chemistry. And this pattern is so important, your next lab, when I come back, it won't be next week, but the week after, that lab, you'll do a whole worksheet, which will be experiment 21 in your lab book, practicing to do these types of reactions we're going to learn. And this is the famous Cub Scout one, because it's Cub Scout yellow, and also it's very dramatic. Any experiment where you get a boom or a dramatic result, like putting salt and water and light up a light bulb, where Cub Scouts go, woo, that's called a Cub Scout reaction in my book. And here, we start out with 2 clear solutions, and then we pour one into the other, and we get a chemical reaction. We get a yellow precipitate. A synonym for precipitate is insoluble, compound, or solid. So those 3 words mean the same thing. Precipitate, insoluble. See here I formed an insoluble compound. It's cloudy and it's going to go to the bottom if it's more dense than the water. So solid, insoluble, or precipitate are synonyms. So when one mixes ions that form compounds that are insoluble, as could be predicted by the solubility guidelines. This is going to be in a table I'm going to teach you how to learn. A precipitate is formed. So this is called a precipitation reaction. And I'm going to write the equation to show you why this happens and what it is in just a second. But these reactions are called metathesis reactions. Metathesis. And metastasize means to transpose. It's a Greek word. And I call them square dancing reactions. You know where they say, do-si-do and switch partners? This is called a double displacement reaction, like you're square dancing and they ask you this, the males from one group and the females from other groups will switch partners. And that's what you're doing in these metathesis reactions. You're switching partners to get a reaction. So, let me teach you, let's learn about metathesis reactions. And let me give you a funny story Oh, there's a pendulum. Let me tell you a funny story why you can't learn chemistry without recognizing patterns. When I took inorganic chemistry as a freshman, when I went to the big school, once again it was overwhelming. There was just so much knowledge, and they didn't really tell us how to study it back then. And I wasn't doing too good at predicting products. They give you reactants, predict products, and balance the equation. So I went to the bookstore and they had a big green box of flashcards. Okay, the tape's wearing out. They had a big green box of flashcards. Flashcards were a big thing then, and there's like 500 cards in there. So they give you a reaction, then you got to predict the products and flip it over and see if you're right. So I bring them to lunch in the cafeteria and stuff. And finally I got discouraged. I go, this is nuts. I can't memorize 500 cards. And then when I got good at chemistry and learned these metathesis reactions and the pattern, I go, oh man, 80% of those reactions were metathesis. So I didn't have to memorize them. There were a pattern there, but I didn't figure it out. So that box was actually pretty good. It stayed in my closet forever, even when I moved. And I go, oh, there's that green box, that worthless green box. But actually, if I had known about metathesis reaction, that box was very doable. I'd only have to memorize 20%. Because in inorganic chemistry, it's hard to predict the patterns of reactivity and find out what the products are. But this one is one of the most predictive reactions there are. Once you learn the pattern that I'm going to teach you about metathesis, you can predict the products and then balance the reaction. So inorganic chemists are very grateful for predicting. In organic chemistry, it's very easy to predict products, okay? But inorganic, it's not. And so I'm just trying to emphasize, you've got to learn this. This is really important. It never goes away, and it's very powerful. Okay, so here's the pattern. AB plus CD. We get a chemical reaction to these two reactants, and we get AD plus CB. And see here, this is a cation. A and C are cations, and B and D are negative anions. And so to react, there's really no reaction here. These are actually aqueous or whatever. And A is going to bump into the oppositely charged D and see if they're a match to make a chemical reaction. And then the cation C is going to bump into B and see if there's a reaction to make that compound, if it's a permanent species. So that's why we call it double displacement. The B is getting displaced from here, and D is getting displaced here, and then do-si-do and form a new partnership and see if we get a reaction. So that's what a metathesis reaction is. The cations and the anions are going with a different partner and see if they form a permanent compound to have a reaction. And to form it, see, for this reaction to occur, if none of these are permanent compounds, we say, oh, no reaction. Even though they try to metastasize, there's no driving force present, so even though they bump into the opposite ions, they don't stay together permanently. They're still just aqueous. So to get a reaction to occur, there's three types of driving forces. Formation of a precipitate. And so if I can put a solid next to that, just like that yellow precipitate forming, I know I have a metathesis reaction. Or formation of a gas. So if one of these ends up being a gas, that's a permanent species, you'll see bubbles in the solution, then once again I know I have a reaction, a metathesis reaction. Or formation of a weak electrolyte. Or formation of water. See, water is a solvent. So if I form water as a product, that's making more solvent. It's also a permanent species, and it's a driving force to have a metathesis reaction. So these are the three driving forces. I'm going to do this one in lecture and teach you how to use the table to predict if something's a solid when it comes together. And we'll do these in lab. Okay, we'll do examples of these in the lab. You're going to do 16 different metathesis reactions in the lab to get good at this. And so I'll save these two for lab. Okay? And this is the most common one. Formation of a precipitate is the most common driving force of a metathesis reaction. So let's do that example where they form that yellow precipitate, and then I'll show you exactly what that is. Okay, they started with lead nitrate, lead 2 nitrate. So one of their solutions in one of the beakers was lead 2 nitrate. They took some lead 2 nitrate, dumped it in, dissolved it in this clear solution. And then in the other beaker, I want to make sure I have room, so I better move this over. In the other beaker, they have potassium iodide. And it's also an aqueous solution of potassium iodide. Those are the two clear solutions in different beakers. Okay? Now they're going to pour one of the beaker solutions into the other. So there's an arrow. And now our task is, if there's a metathesis reaction, we want to give them what's called the net ionic equation of the metathesis reaction. Net ionic equation. So to do that, we're going to use 3 steps. And so you have to learn this 3-step pattern that if you do have a metathesis reaction, you've got to give the balanced net ionic equation. And so this is going to be the first reaction, if we have a reaction. This one we're going to call the balanced. Ooh, I don't want to write it there. Oh well, balanced molecular equation. We're going to pretend these are molecules at first and they don't break apart in water. The reason why we're doing that, we're just trying to see, first of all, do we have a metathesis? Do we have a driving force? Do we make a driving force as a product? And number 2, we want to balance it together. And then we're going to go ahead and break apart the ones that really broke apart in solution and get to the net ionic reaction. So here's how I do it. And once again, this is a really good pattern. If you follow it, you won't make mistakes. If you make any mistake in the pattern, it's all going to blow apart. And so students like to do it their own ways, that's fine. This is the most basic way. If you do it my way, you're not going to make mistakes. You can do it your way, that's your freedom, but good luck. The way I do it, you know this is a salt, metal, cation, anion, cation, anion. So what I'm going to do first before I start, I want to dose-I-do. So I want to identify the cations and the anions. I don't care how many of them there are at first. I just want to identify one of them each. So I know from chapter 2 that this is lead 2+. So I'm going to write it right above it. I want to know exactly what the cation is. And I know it's lead 2+ because I uncross over this 2, it's lead 2+. And then I know by now this is just nitrate. It's from that common ion table, but nitrate's one of the most common polyatomic anions. You should actually be pretty familiar with it by now. And now over here, I know this is potassium plus, 1+, because it's a group 1A alkali metal. All alkali metals as cations are 1+. And then this is iodide, I1 negative. And once again, that's group 7A, so I shouldn't even have to look at the table now. All 7As, when they form salts, or anions to form the salts, are 1 negatives. Okay? So once again, it's really important to know what the ions are. You look at the neutral formula, they don't show you the charge, but now you got to show 1 ion of each with the charges. Okay, that's where you start. And now we're going to dose-I-do. And so now I'm going to switch partners. I'm going to take my lead cation and I'm going to react it with the other anion, iodide. See, there's one displacement right there. They bump in solution once I mix them into the opposite ion. And then the potassium, its square dancing new partner, when you change partners, it's going to be nitrate. So see what I did there on the product side? Lead's going to bump into iodide to see if we have a driving force for metathesis, and potassium's going to bump into nitrate. So I switched them. I did my square dancing, do-si-do, and then exchange partners. Okay? So that, if you do this part right, you're probably going to get the thing right. If you can't identify the ions, you're going to have a hard time doing these. Okay? Now, I'm going to pretend there's a reaction. I want to bring these down as a neutral formula. I'm going to pretend that they do react and form a permanent species. So I use the crossover method. And I know that neutral formula, those ions would be PbI2. And then this one's 1-to-1, the charges, so it would be KNO3. And I put a plus between them because now it's part of the equation. These are just, they're not part of the equation, they're just, give me the ions. But you want to put these on the equation line. Because if there is a metathesis, those are the species that I will form. And now here's what I have to do. Now I have to figure out what the physical state is, see if it's a driving force. And this one's to see if we have a precipitate. So they don't, I don't have this on a PowerPoint. So now you need to turn to page 121 in your text, page 121. And there's a solubility table, table 4.1. And it's got 4 areas in this table. It's divided into 4 areas. Okay? And they list anions in each area of the table. We've got nitrate, acetate, nitrate, acetate, chloride, bromide, iodide, and sulfate. And here it says soluble. And these are exceptions. Insoluble. Okay. And then down here it says insoluble. And they've got some anions there. Sulfide, carbonate, phosphate. Sulfide, carbonate, phosphate. And then one more, hydroxide. And then here it says exceptions, none. And I believe acetate exceptions, none. Now, all the halogens, these 3 halogens, halides, the exceptions are silver, cation, mercury 1, cation, and lead 2, cation. So all 3 of these right here, chloride, bromide, iodide, have the same exceptions. And then sulfate, the exceptions are strontium, barium, mercury 1, and lead 2. Okay. And let's just do one set of exceptions down below. Let's do carbonate, ammonium, and all alkali metal cations. i.e. K+, Na+, etc. Okay. So here's what you want to do in your notes. You want to put aqueous here. That block, if your compound falls in this block, according to the rules, it means it's not a driving force. It's aqueous. For example, you identify your new compound, you look at the anion. You know that's nitrate, right? That potassium, the anion of the salt we're trying to form is nitrate. So you look at nitrate in the table. Nitrate. And that means all nitrates, whatever the cation is, will be soluble. Aqueous, not a driving force. Exception, the exception would be solid, insoluble. Oh, there are no exceptions. All nitrates are soluble. So here we write aqueous. And that is not a driving force, okay? Aqueous salts are never driving forces. So these are aqueous salts. They're giving you anion, and all cations except the exceptions are aqueous. But if it's an exception, then it's a solid, insoluble, and then it is a driving force. It is a driving force. So let's look at this compound. The anion's iodide. So here's iodide right here. So all iodide salts are aqueous, not driving forces. Oh, let's look at the exceptions. Silver iodide is a driving force, it's a solid. Mercury 1 iodide is a driving force. Oh, look, lead. Lead iodide's an exception. It is a driving force. So here we put solid. And I put a star here, asterisk, because it's a driving force. So therefore I have a metathesis reaction. Because the precipitation table told me that. And we're not going to use this one here. These are all solids. Salts of these anions are always solid, okay? And so they are driving force if you form any of these salts. But the exceptions are aqueous. They're not driving forces. So for example, if we formed ammonium carbonate, it's not a driving force because it's an exception to be aqueous. If we formed potassium carbonate, once again, it's an exception to carbonate, so it would not be a driving force, it'd be aqueous. But if we formed calcium carbonate, oh, it'd be a solid. It'd be a driving force. So you'll get to use this table a lot in the lab when we do the metathesis worksheet. And you have to understand this table. And I gave you this table on the table sheet for the exams. So you don't have to memorize it, but you have to know how to read it and use it. Okay? And so in lab, a lot of people have a hard time at first getting to learn how to use this table, so make sure you ask questions until you understand how to use it. And this is once again to use the first driving force, see if you get a precipitate. Okay, now I'm going to erase this, and then I'm going to go ahead and continue with this reaction here to do a complete metathesis reaction. Okay, once you have a reaction, I've already made the formulas, and now I have a driving force, so now I have to balance it. And so on this one, well, I'm sorry, I made a mistake here. I'm sure you caught it by now, but you didn't get to talk, did you? This should be Ki, because 1 and 1, it's not Ki2, it's just Ki. Okay. And now, since I have 2 iodides here, I got to put a 2 over here to get 2 iodides. And now I have 2 potassium here, so I got to put a 2 here to get 2 potassium. And now it's balanced. I have 1 lead, 1 lead. 2 nitrates, 2 nitrates. 2 potassium, 2 potassium, 2 iodides, 2 iodides, and it's balanced. So don't forget to balance when you go to the next steps to get our net ionic. So now here's the next step, number 2. This one's called the complete ionic equation. The complete ionic equation. It's not the net ionic yet, but we have to go through the complete before we can get our desired net ionic equation. So here's what you do next. Once you have your balanced molecular, see, if you don't get any driving force, you're done. You just put NR, no reaction. You don't even have to balance or anything. You just say, oh, no reaction. But here we do have a reaction, so we continue. And so now I'm going to pull apart all my aqueous strong electrolytes because they're really pulled apart in a solution. Okay, they're not a unit, they pulled apart. Never pull apart a driving force. Never pull apart a solid. Never pull apart the solvent, liquid water. Okay? So once again, we want to pull apart all aqueous strong electrolytes for the second step. That's all you pull apart. Not aqueous. If you have an aqueous weak electrolyte, don't pull it apart. Like acetic acid, even though it's aqueous, you don't pull apart a weak base or weak acid, even though they're aqueous. You only pull apart aqueous strong electrolytes. And these are the strong acids, strong bases, and the salts, ionic compounds. So ionic, aqueous, acid, strong acid, aqueous, those 7, and the strong base, bases, aqueous. These are the ones you memorize in that table, the 7 strong acids and the hydroxides that are strong. And these are any salt with aqueous you're going to pull apart. Don't pull apart anything else. Okay? Pull apart all aqueous strong electrolytes, which are ionic compounds, aqueous, strong acid, aqueous, and strong bases, aqueous. So that's what you have to do for step 2. Okay, so let's do it. Oh, aqueous ionic compound. I check it. Oh, I have to pull it apart. Aqueous ionic compound. Pull it apart. Oh, solid. Never pull apart a solid. Even if it's a reactant, don't pull it apart. Oh, aqueous ionic compound. Pull it apart. And now when you pull it apart, the number matters. It has to be balanced all the way down. So you can't just put the ion. You got to say how many of them there are from the balanced equation. And so the cool thing about this, you already know what the ions are. Since I'm pulling this apart, they're going to become lead 2 ions and nitrate ions. So you've already identified the ions if you have to pull apart. See? And they're aqueous because they came from aqueous, so in the second step I'm not going to write aqueous, I'm too lazy. But now there's 1 times 1, 1 lead. And there's 1 times 2, there's 2 nitrates. So I got to put a 2 here, 1 times 2 nitrates. And now it's balanced. 1 formula unit of this form 1 lead and 2 nitrates by pulling it apart. And now I do the same thing here. I'm going to have potassiums and iodides. Because I already identified the ions if they pull apart up top. And I have 2 potassium and 2 iodides. See that? 2 times 1, 2 times 1. So there, and usually you're going to pull apart all your reactants except weak acids, weak bases, and solids. You can have a solid in the reactant and still get a metathesis. Okay? And now you never pull apart your driving force, it's permanent. So I'm going to bring that down as is and put the solid there because that's my driving force. And now, once again, I'm going to pull this apart. I termed it, and it's going to become potassium and nitrate. The ions I already wrote. And now I have to do it stoichiometrically. 2 times 1 is 2 potassiums. 2 times 1, 2 nitrates. So now I completed step 2. All you do in step 2 is pull apart all aqueous strong electrolytes. Strong acids, strong bases, and ionic compounds that are aqueous. And you pull them apart stoichiometrically. And once again, you pull them apart with the ions you already identified. But don't pull apart weak acids, weak bases, and solids. So there's my complete ionic equation. And this is what really exists in my beaker now. In my beaker, the leads are going to react with the iodides to form the cloudy. This is the cloudy yellow compound that you saw in the beaker. And then these are just floating. These are called spectators. The spectators are in the beaker, but they're not part of the chemical reaction. It's like a football game. You've got the players on the field and the spectators in the stands. And with chemists, they don't want the spectators. They're there in the beaker, but they're not part of the reaction. And that's why with metathesis, they want the net ionic equation. That just identifies the players. They don't care about the spectators. So here's how you determine the spectators. This is an algebraic equation now, and this is an equal sign. So we're allowed to use algebra to simplify. And so here, anything that's the same on both sides, we can subtract it out, they go to 0. We'll subtract out the spectators. So here we're going to subtract 2 potassium, both sides, we cross it out. They're really there, but they're spectators, we cross them out. Subtract 2 nitrates from each side, boom, the nitrates are gone. They're spectators. And now we can't cross out anything else because the lead 2+ is a PbI2 solid here. They're not the same. And iodide is not iodide over here, it's in a compound, a solid. So now you bring everything else down, and that's called the net ionic equation. And this is why we're doing the whole thing. This is what we want, the net ionic equation. And the net ionic equation has to be perfect. You've got to put every physical state, balanced equation, and show all the players in the reaction. And that's easy, because all you do is pull down the things that aren't crossed out, and that's a net ionic equation. So, and you want to put the cation first, okay, the cation first. So here we bring down lead 2+, aqueous, because now we got to put all the physical states, and it's aqueous because it came from an aqueous before we pulled it apart. And don't forget the charge. A lot of students will pull these down and forget the charge. Then it's a metal. It's a metal. It's neutral. That's totally different than a cation. And then we pull down iodide, and we write aqueous because it came from an aqueous compound. So on the reactant side, now in the net ionic, we have 2 reactants. And then when they came together, they formed a precipitate. PbI2, solid. And that's the yellow precipitate you saw in the beaker when you mix those 2 clear solutions. Okay? So here's our net ionic equation. 1 mole of lead 2 ions combines with 2 moles of iodide ions to form 1 mole of lead iodide, precipitate, or solid. So this is your first metathesis reaction. And once again, I'll finish the rest in lab. Okay, we'll do a lot in lab. And so I'm just going to do 1 here in lecture, and then maybe I ought to do 2 more, since I won't see you next week. And you might be trying to do chapter 4 homework. I guess I better do the gas one and a weak electrolyte one. So I lied. If we were having lecture next week, I'd stop here and do the rest from lab. But since I'm not going to be there next week, and you might want to get ahead and finish your chapter 4 homework, I better show you how to do a gas one and a weak electrolyte one. Okay, once again, this would say if a metathesis reaction occurs, give me the balanced molecular, the complete and net ionic equations. If not, put no reaction. Okay, this is an acid, and this is a base, a hydroxide base. So this is called a neutralization reaction. A neutralization reaction. Okay, because we're going to react the acid with the base and get a salt and water. We'll have no limiting reagent, and no excess reagent. All the reactants will be consumed, and we won't have an acid or base anymore, because it'll be water plus a salt. And so here, the cation in an acid is H+. So whenever you're doing metathesis and you have an acid, write H+ above the cation. And then once again we have chloride here, monatomic chloride. And now we have sodium plus and hydroxide. Those are the ions in those formulas. And now we do-si-do, switch partners. So the H plus is going to go with the OH negative, and the sodium plus is going to go with the chloride. So just like any metathesis reaction, we switch partners. And now the next step, we bring them down with a neutral formula. And HOH is water. Whenever you form water, it's a solvent, you put L, liquid. You're telling them to solve it. And then when we bring this down, the neutral formula is sodium chloride, table salt. Whoops. And so you don't even have to look in the table here. Whenever you get an alkali metal salt, it's always aqueous, always insoluble. All alkali metal salts are soluble, aqueous. They are not driving forces. So I put aqueous. Here's the driving force. Whenever you form water, solvent, it is a driving force. It's a permanent species that stays together. Okay? So now I balance it, and it's 1, 1, 1, 1. When all you have 1 plus is 1 negative switching, it's always going to be 1, 1, 1, 1. So there's my balanced molecular equation. Okay, number 2, I'm going to pull apart all strong aqueous electrolytes. Oh, strong acid, aqueous, pull it apart. Strong base, aqueous, pull it apart. Oh, driving force. Don't never pull apart a driving force. Aqueous salt, pull it apart. It's a strong electrolyte. So now I already know the ions. So I'm going to put an H plus here and a chloride. And now a sodium ion and a hydroxide. And they're all ones, 1 times 1s. And then, oh, bring down my water as is. And then pull this one apart. Na plus chloride. So you already know what they are. So there's my total ionic equation for this one. And now remember, to get the net ionic, I call it the net ionic, Ni. I want to cross out my spectators. The ones are the same on both sides. So here I can subtract 1 sodium ion from each side, and I can subtract 1 chloride ion from each side. And I bring all the ones down that didn't cross out. H plus aqueous, because it came from an aqueous, plus hydroxide, came from an aqueous, gives water. So there's my net ionic equation for a strong acid, strong base neutralization metathesis reaction. And this is the same net ionic equation for any strong acid, strong base neutralization reaction. The proton of the strong acid reacts with the hydroxide of the strong base to give water. And see, the cation here and the anion here will always be spectators. Okay? So this is the famous neutralization reaction. HCl plus NaOH. Okay? I'll do 2 more metathesis reactions for you. And watch, we'll just leave 1, 2, 3, because if we have a reaction, we're always going to have 3 steps. Now I'll show you a formation of a gas, the famous one. We'll take sodium carbonate, plus HCl. So we're going to see if we have a metathesis reaction here, and if we do, we're going to get the net ionic equation. So first of all, identify the ions in each formula. And I have sodium ion and carbonate. And here, oh, it's an acid, so I have an H plus and then a Cl negative. Okay? And now I'm going to do-si-do and alamine left and switch partners. So the sodium is going to bump into the chloride, and the proton is going to bump into the carbonate. Okay, and now I bring them down as neutral formulas. I pretend there's a reaction. So NaCl plus H2CO3, H2CO3, because the 2 goes here and the 1 goes there. Okay. And once again, you know that this one's not a driving force, because all alkali metal salts are soluble, aqueous. Aha, this is an acid. See, this is an acidic proton. Whenever you get an acidic proton switching partners, you're going to form an acid. And this is a weak acid. It's a driving force. A weak acid, because it's not one of the 7. And if you take an AMP or biology, that's carbonic acid. It's one of the buffer systems in our body. It's part of one of the buffer systems. So now we know we have a driving force. And this one, since it's weak acid, all weak acids you can put aqueous, okay, because those came from aqueous ions. And they're not going to precipitate. But you formed a weak acid, so it's going to be permanent. It's going to ionize a little bit, but stay mostly together. And now we balance it. Oh, we have 2 sodiums here, so we need a 2 there. We have 2 chlorides there, we need a 2 there, and it's balanced. 1, 2, 2, 1. Okay, once we balance, this one's tricky. When I bring this driving force down, cross it off. I'm going to write CO2 gas plus water. And you go, how do I know to do that? I go, memorize it. When carbonic acid is formed, it spontaneously decomposes into 2 driving forces, CO2 gas, you'll see bubbles in the solution, and water. Once again, how do I know that? You memorize it. I just told you. In fact, they've never isolated carbonic acid. Never isolated. They can find the water and the carbon dioxide gas. It's a fictitious weak acid. And we write it just for logical purposes. But nobody's ever isolated carbonic acid. So you just cross it off after you balance, and then write water and CO2. And once again, it's stoichiometric. You got 2 H's, 2 H's, 3 O's, 2 here, 1 here, 3 O's, 1 carbon, 1 carbon. So 1 carbonic acid forms 1 CO2 plus 1 water. And so this is formation of a gas. You didn't see it at first. You have to memorize when you form the weak acid carbonic, which is aqueous. You automatically change it to CO2 gas and water, liquid. Okay. Now we're going to pull this one apart. Aqueous salt. Oh, strong acid. Aqueous, pull it apart. Aqueous salt, pull it apart. And this one we read down as CO2 and water, the driving forces. So let's pull them apart. And you already know the pull apart ions are the same ones we wrote above it. I had to have a little more room here. Okay, and then I have to do it stoichiometrically. 1 times 2 sodium ions, 1 times 1 carbonate, 2 times 1 for 2 protons, H+, and 2 times 1, 2 chlorides. Okay, so 2, 1, 2, 2. And then the sodium here, 2 times 1 for 2, 2 times 1 for 2. Okay, now we're done with the total ionic. So now we cross out spectators, subtract 2 sodium ions from both sides, and 2 chlorides. Bring down the uncrossed over ones, and let's put the cation first. It looks better. Came from aqueous, so it's aqueous. So there, the reactant ones that come down, 2 protons or 2 H pluses. It's a proton because it's protium. We lost the electrons, just 1 proton in the nucleus. Plus carbonate gives CO2 gas plus water liquid. This is a very famous equation. Very famous. You take a carbonate, salt, and any acid, you're going to get CO2 and water. And once again, students will say, how am I supposed to do that? Because you memorize this goes to this. And it's in your lab book too. I'll show it to you when we get in lab. Okay, I'll do one more. Okay, I'm going to take sodium acetate, which is an aqueous salt, and I'm going to react it with HCl. Okay, so on an exam or quiz, it look like that. They say if there's a metathesis reaction, give me the balanced molecular, complete ionic, net ionic equations. If not, write no reaction. So here I have Na+, and I have acetate, and here I have H+ and chloride. Identified all the ions. Remember, this is an acidic proton. Now sodium is going to bump into chloride. The acidic proton's going to bump into acetate. Then bring them down as a neutral formula when they switch partners. And this one is not a driving force because once again, alkali, metal, salt are always soluble. On this one, you know it's an acid because it came from an acidic proton bumped into an anion. So an acidic proton is always going to make another acid when you switch. But here, is it one of the 7 strong acids? No, it's a weak acid. So you put aqueous, and we don't pull it apart because it's a driving force. It's a permanent species, a little bit of ions ionized, but that's a permanent species. So it's a driving force. So don't pull that apart because it's a weak acid. And it's not a solid. If you look on the solubility table, it says all acetates are soluble, no exceptions, but this is not, that's for salts only. That table 4.1 is a solubility table for salts, not for acids. So a lot of students will put solid here and I go, where did they get the solid from? Oh, they're looking at the salt table. But this is not a salt. This is not soluble. It's a weak acid, weak electrolyte, so it's aqueous. And now we pull apart the ones we can. This one, salt, strong acid, salt. So this is going to be sodium ions. This can be acetate. I already know what they are up here. H+ and chloride. Sodium ion again. Chloride. And driving force. And it's already balanced because they're all ones. The charges are all ones, plus 1 negative, so I already knew it was balanced, 1, 1, 1, 1. So there's my complete ionic equation. So next, I cross off the spectators, the ones I can algebraically subtract from each side. Subtract 1 sodium from each side, subtract 1 chloride from each side, and then bring down the rest, put the cation first. And there's my net ionic equation. So this was an example when you form a weak electrolyte as a product to get a metathesis reaction. Here we formed a weak acid. And students will end up pulling this apart. You can't, remember? You can't pull apart weak electrolytes. Only strong electrolytes that are aqueous, which is strong acid, strong base, and ionic aqueous. Okay. So now we've finished the lecture part of metathesis. We'll do the rest in lab. So if you look at your outline, the next thing under, we did a neutralization reaction, but now we're actually going to define acids and bases. Okay. I'm going to do the first step. It says define acids and bases. And actually, when we do a titration in the lab, we're going to learn more about acids and bases in lab when we do our titration experiment, which will be the week after we do the metathesis. So let's learn a little bit more about acids and bases. Okay. Okay. We're going to learn two definitions of acids and bases, Arrhenius and Bronsted-Lowry. Bronsted-Lowry. There's actually three definitions, and we don't learn the third definition until Chem 122. But the Swedish, they knew what acids were, they knew properties of acids, but they didn't know chemically where the properties were coming from. For example, all acids taste sour, etc. And Arrhenius said, oh, here's what an acid is. It's a substance that when it's dissolved in water, it increases the concentration of H+. See? When you dissolve that substance in water, it increases H+. Therefore, it's called an acid. So that's the Arrhenius definition of acid, which is the simplest definition. Okay, the organic chemists like this definition better, Bronsted-Lowry. They define an acid as a proton donor, an H+ donor. So when it participates in a reaction, it loses an H+. It donates an H+ to another compound. The other compound takes the H+. So once again, Arrhenius definition of acid, a substance when it dissolves in water increases the H+ concentration in the water. Bronsted-Lowry definition, an acid is a proton donor, H+ donor in a chemical reaction. And here's some space-filling models, some acids. Here's HCl, this is acidic proton. Here we have nitric acid, NO3H, NO3, and here's the acidic proton attached to the oxygen. And then here's our buddy acetic acid, written the organic chemistry way, CH3COOH, weak acid. So here you have the CH3 and C double bond OH. And these are the color codes you should know of. These are universal color codes of these atoms. Carbon's always black, oxygen's always red, nitrogen's always blue, chlorine's always green, and hydrogen's always white. That's an international color code for those atoms and models. Okay, and acids, they taste sour. Okay, we shouldn't taste them all, but things that are sour are acidic. Okay, let's talk about bases. Once again, there's an Arrhenius definition and a Bronsted-Lowry definition. The Arrhenius definition is the substance when it dissolves in water increases hydroxide ion concentration, which is OH negative, hydroxide. Where a Bronsted-Lowry definition is a proton acceptor. It got it from the acid. It will accept an H+ from an acid. Proton acceptor, H+. And another property of acids and bases, there's a compound called litmus, and you can put it on filter paper. Okay, and there's two types of litmus. There's red litmus paper and there's blue litmus paper. See, this is blue litmus paper that hasn't been changed. This is red. And a base turns litmus paper blue. It turns red litmus paper blue. So you go ahead and put both litmus papers in your solution. And in here, the blue one would stay blue. So we put the blue one in here too, it'd stay blue. But the red one would turn blue. And that means it's a base. So litmus is a pH indicator. And then if you put the litmus papers, both of them in there, in an acid, if you put blue litmus and red litmus paper in here, an acid turns blue litmus paper red. And the red litmus paper would stay red. Okay, so we've got litmus paper in the lab, and we'll do that when we do our titration, learn about acids and bases. We'll test solutions with litmus paper to see if they're acids and bases. But once again, a base turns red litmus paper blue, and an acid turns red, blue litmus paper red. And we already learned the strong bases, right? The alkali metal hydroxides and calcium, strontium, and barium alkaline earth hydroxides. And we'll do this in lab. So you already did this one, right? Sure enough, we get the same net ionic equation, H plus OH negative. This is the example I showed you for neutralization, strong acid plus strong base, net ionic. Okay, we already did this one in the notes. And, we did sodium carbonate, they're doing calcium carbonate, and we'll do that one later. That's chalk. Okay, I'm going to start a new type of reaction, and this is called single displacement. And I'm just going to introduce this because I made another tape to finish redox reactions. And so this tape is going to end when I explain the activity series with oxidation half reactions. And then there'll be another YouTube video that will go. There's actually 2 more that finish chapter 4. But this one's actually 1 lecture. So for my Fallon class for next week, you only have to listen to this lecture. But if you want to listen to the other YouTube sites that finish chapter 4 to be ahead, I'll give you those URLs also, and then we'll go over those in the lecture I come back, okay? But if you want to get ahead, you can actually watch those too, and you'll be done with chapter 4 by listening, and you'll know how to do all your homework. Okay. So this is another type of reaction we're going to introduce in chapter 4. And this one's called single displacement. And before we can do these, we have to learn what oxidation and reduction reactions are. And so I'm going to teach you oxidation, reduction reactions. These are not all reactions are oxidation reduction reactions, but here you get electron exchange. Electron exchange. And for short, they call them redox reactions. Redox. Reduction, oxidation reactions. Redox. And these are really important reactions to understand, especially in biochemistry, because if you take an A&P or biology courses, when we get energy from our food to survive, to keep our homeostasis in our body going, all those reactions extracting the energy out of the food are redox reactions to make the ATP, which is the energy currency of the cell. And so we use redox reactions a lot in our body to keep us alive. And if you ever become a biochemist, you'll have to understand every little step and all the energy transformations and everything. And this is where it starts, understanding the electron flow. Okay. In a redox reaction, you do not see the electrons. In the balanced equation. Because they cancel mathematically. Electrons lost from the reactants equal electrons gained. Okay. I'm sorry, electrons lost equal electrons gained in the redox reaction. So they cancel out, so they don't put them in the net reaction. So we're going to learn what's called oxidation numbers. By learning oxidation numbers, we can see if we have a redox reaction. Okay, because then we'll see the electrons by the oxidation assigned numbers. And so that's what we're going to do first. Before we actually study the redox reactions and use this activity series, we've got to learn what oxidation numbers are and how to assign them to every atom in a balanced chemical equation. So there are a lot of rules in your textbook to assign oxidation numbers to atoms. And these rules are found on page 132. So you need to look in your book now on page 132. And they give 4 rules on page 132 how to assign oxidation numbers to atoms. And these rules, I'll give you the table. You just have to know how to read it and interpret them. And I'm going to go ahead and show the PowerPoint with the rules. The book's actually a little better organized showing them, but the PowerPoint will also go over all the rules. Whoops. Gotta find out where I put the changer. Not in that pocket. I must have set it down. Oh, got ahead of myself. Let me teach you the definitions of oxidation reduction. Oxidation, there's 3 definitions. Okay, I'll give you the simplest one first. It's called the gain of oxygen bonds. So when you take a compound and you go from reactant to product, if it gains oxygen bonds as you make a new product, it's being oxidized. Okay, that's where oxidation came from, oxygen. And usually it's on a carbon, but not always. Or then the second definition they came up with is when you oxidize, you lose hydrogen bonds, lose bonds to hydrogen. Your compound loses bonds of hydrogen as it goes from reactant to product. It's also being oxidized. And then the best definition, when you're oxidized, you lose electrons. But you can't see the electrons because they cancel, but as you go from reactants to products, an atom in some formula is losing electrons. That's the best definition of oxidation, the loss of electrons. Okay, the gain of oxygen bonds, the gain of oxygen atoms in a compound, the loss of bonds of hydrogen, or the loss of electrons. Now let's go over the 3 definitions of reduction. Reduction. And the reason I'm giving you all 3 definitions, the book just gives you the electron definition, but if you're going to be an allied health person going to biochemistry or medicine or nursing, you're going to have to know all 3 definitions, because the chemists like the electron definition the best because it's the most complete. But a lot of times you take a biology class or organic class, they're going to use the oxygen-hydrogen definition. So reduction is the loss of bonds to oxygens in a compound. The loss of bonds to oxygen as you go from reactant to product. So the opposite of oxidation. The gain of hydrogen atoms. The gain of hydrogen atoms to a compound as you go from reactants to products. Once again, the opposite. And then the gain of electrons. So these are the opposite of the oxidation definitions in the proper order. Loss of bonds to oxygen in a reaction, gain of hydrogen atoms in a compound, or gain of electrons in an atom, going from reactants to products. Okay. Now I'm going to show you a famous series of oxidation reductions. So we're going to start with 1 carbon compounds. This is methane, the simplest organic molecule. Met means 1 carbon. CH4. And this is a fully reduced compound because carbon can only have 4 bonds. And here it's neutral. And all 4 of those bonds are to hydrogen. So this is a fully reduced compound. And fully reduced compounds are very high in energy. They will stoke a fire. If you light them, they'll burn. Stoke a fire. Keep the fire going. And so it's the carbon-hydrogen bonds are very rich in energy. Okay? So this is the most reduced form of 1 carbon compounds. So now we're going to oxidize this 1 step at a time until it's fully oxidized. So now this compound's methane. This is methanol. And you don't have to know these names except for methane, but some of you will recognize them. This is an alcohol, that OH. And we still have 4 bonds, but we're talking about the bonds to carbon. And by one definition, this is more oxidized, right? Because now we've got, of the 4 bonds to carbon, one of them is a carbon-oxygen bond. And when you put an oxygen on carbon, that means it's more oxidized. Even though we still have the same hydrogens, the hydrogen's not on the carbon, one of the 4 bonds on carbon. So this still has energy in it. These 3 bonds are still energetic, but it's not as energetic, much energy as methane. So we'll oxidize another step. This is formaldehyde. Formaldehyde. And once again, of the 4 bonds to carbon, 2 of them are to oxygen. This is a double bond, only 2 hydrogens. So this is more oxidized than this. Okay, next. This is formic acid. Formic acid. Once again, of the 4 bonds to carbon, 3 of them to oxygens and 1 to hydrogen. So this is even more oxidized. And then we have the one you're all familiar with, carbon dioxide. Now, all 4 of the bonds to carbon are oxygen, so it's fully oxidized. We can't oxidize it anymore. Fully oxidized. And so you should know these structures, and I should be able to give you 2 of them and say which one's more reduced or which one's more oxidized. Because you can go either direction. You can start here and go backwards and reduce it 1 step at a time, or oxidize it. And this is a famous question. Be able to recognize 2 of these molecules and say which one's more oxidized, which one's more reduced. Remember, the more hydrogens on the carbon, the more reduced. The more oxygens on the carbon of the 4 bonds, more oxidized. And fully oxidized compounds, they put out fires. So this is fully oxidized. They'll actually put fires out. Because they're low in energy. See, they're low in energy, very low in energy. So now you kind of have a feel for oxidation reduction. Okay. So now we're going to go back to those. Now we're ready to do the oxidation numbers. Okay. Give me another second to write down these compounds. And we're almost finished. Okay, now we're going to do the oxidation numbers. And we'll look at the rules. I might want to just give you some examples. Okay, so here's why we're learning the oxidation numbers. To determine if an oxidation-reduction reaction has occurred, we assign an oxidation number to each element in a neutral compound or charged entity in our balanced equation. To determine if an oxidation-reduction reaction has occurred, we assign an oxidation number to each element in a neutral compound or charged entity. So to each atom of an element, each atom. And here's how we do it. These are the rules on page 132. Elements in their elemental form have an oxidation number of 0. Remember those gases that are diatomic elemental form? These would all have 0 oxidation numbers on each atom. So here there's 2 atoms, but each one of those oxygen atoms has a 0 because it's elemental form. Elemental form 0, chlorine 0. Or if you get a metal where they show 1 atom of the metal with a solid, that represents a big chunk of metal. Okay, it's like the empirical formula. So any metal would get a 0 oxidation number, and these diatomic species we learned would get 0 oxidation numbers because those are elemental form. Okay, the oxidation number of a monatomic ion is the same as its charge. The oxidation number of a monatomic ion is the same as its charge. So there's a monatomic ion, and so this would be a +1 oxidation number. And once again, charge, with charge we write 1 plus, we don't write the 1. This is charge. Oxidation number is +1. That's how they differentiate between these two numbers. Charge is always a number first, then the sign. Oxidation number is a sign first, then the number. Okay, that's why we're going to learn charge, whereas with 2 negative or +3. Those are, 3 plus. 3 plus, 2 plus, 1 plus, 2 negative, those are charges. +1, -5, those are oxidation numbers. So if we have a compound like calcium chloride, that's made up of 2 monatomic ions. Just like we identified ions, it's a calcium ion and a chloride. It's just a neutral formula in a balanced reaction, CaCl2. So this calcium would be a +2 because it's a monatomic ion, and the chloride's a -1, or just a negative because it's chloride, monatomic ion. So that's that rule. Okay, whoops. Got our swinging, the pit and the pendulum. I almost got my head crashed in. A wrecking ball. Quit wrecking my lecture. Okay, nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. Oxygen has an oxidation number of -2, except in the peroxide ion, which has an oxidation number -1. There's also a -1/2. You can have fractional oxidation numbers. And in our homework and in our course, any oxygen I give you in a compound is going to be mostly a -2, but not always. I'll leave the peroxide one and the superoxide, which is a -1/2 oxygen for Chem 122. But there might be one in your homework, tell me about it, I'll give you back the points. But on an exam I wouldn't give you one. Okay, hydrogen is -1 when bonded to a metal, because now it's a salt, a hydride, and it's a +1 when bonded to a nonmetal, like carbon, or an acidic proton is a +1. So hydrogen is mostly a +1, every once in a while a -1. Only when it's with a metal first and a salt. Oh boy, my tape isn't sticky anymore. I think I'm out of luck. Oh, no wonder they had this tied up before. Oh well, I'll fix it in a minute. I'm getting tired just like you. Okay, let's take a break. I'll fix the screen and then we'll continue. Okay, once again, these are in your book, and I'll give you some examples in a minute. Okay, nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds. Fluorine's always a -1. Fluorine's always a -1, except in F2, it's a 0, but in a compound, it's -1. The other halogens have an oxidation number of -1 when they're negative, but they can have positive oxidation numbers. However, most notably when they're in oxyanions, like chlorate, ClO3 negative, then the chlorine's going to have a positive oxidation number. The sum of the oxidation numbers in a neutral compound is 0. The sum of the oxidation numbers in a polyatomic ion is the charge on the ion. And once again, you don't have to write these down, they're in your book on page 132. And then I'm going to do a lot of examples and I'll refer to those rules. And that's how you learn them, by doing examples. Okay? So let's do some examples. Let's take sulfate, SO42 negative. And then we have to assign an oxidation number to each atom, per one atom. So each sulfur, there's only one in each oxygen. So here we're going to use an attic, like in a house on the main floor in an attic. The attic are the totals. And remember, the one rule said, with a polyatomic anion, the total oxidation numbers equal the charge on the species. So we're going to call it -2 because we're adding oxidation numbers. These are total charges in the attic, and these are individual. And it's the individual ones we want. We're just using totals to get the individual. And most of the time, oxygen's always a -2, except in O2 it's a 0. So that's the known. And when you determine oxidation numbers, sometimes you'll know all the oxidation numbers in a formula because they're in the rules. But a lot of times, especially in polyatomics, one will be an unknown, it can change. And by using the attic total method, we can come down back to the regular floor and get the charge on the unknown. So, to go up, we multiply. 2 times 4, there's 4 oxygens at -2 apiece. So the total charge, the total oxidation numbers in sulfate is 4 times -2. This is per one atom. And so now we say what plus -8 gives -2? Oh, we go +6, right? +6 plus -8 is -2. And that's why we have the total, because we can figure out the unknown. There'll be one unknown. And now when you come down, back to the floor, you divide. So here we go, 6 divided by 1, and we get +6. And these are the oxidation numbers, the ones on the normal floor. And so once again, when you go up, you go oxidation number times subscript. When you come down, total oxidation number divided by subscript. So now we know in sulfate, the sulfur is a +6 sulfur, and each oxygen is a -2. Okay, so there we use the rules to get the oxidation number on each atom. Okay, let's do glucose. C6H12O6. See, here we have 3 types of atoms, so we're going to have 3 compartments. Okay, we do our addict method. And here it's a neutral molecule, so the sum of the totals, oxidation number, is going to be 0 because the molecule is neutral. That's one of the rules. And once again, oxygens and compounds in this class are going to be -2s. Hydrogens is a +1. The only time a hydrogen is not a +1 is when it's a salt. This is a H-, and we could even put calcium hydride. See, a 2 goes here and a 1 negative here. These are called hydrides or salts, and these are -1 hydrogens. See. But other hydrogens, except for H2 is a 0, other hydrogens and compounds, even acidic hydrogens, are +1, the most common. So those are 2 knowns, and this is our unknown. So now we go up. 6 times -2 is -12. Okay. 12 times +1 is +12. And now we say, what plus 12 minus 12 equals 0? Oh, 0. We already have a 0. With +12 and -12 when we add them. And so we get 0. 0 divided by 6 is 0. You can have 0 oxidation numbers just like the elemental forms. And so here are the oxidation numbers. This line here. Each carbon is a 0, each hydrogen is a +1, and each oxygen is a -2. So you got to use the rules and then an unknown with the addict to calculate the oxidation number on the unknown. So let's keep practicing some of these. Let's go AsO4 negative. How about 3 negative? And AsO3 negative. This is arsenate and arsenite. And the reason I picked these, I want to explain the arsenic and Fallon water. So here we do our addict, and here we do our addict. So here we have a -2 oxygen and a -2 oxygen. Okay. And now we have 4 of those, so this will be a -8, and it'll add to -3 because the charge on the polyatomic is 3 negative. And now we say, what plus -8 equal -3? Oh, +5. And with the oxidation numbers, you have to write the plus or negative. You can't just write 5. And now we divide coming down by the subscript. 5 divided by 1 is a +5. So here are the oxidation numbers in arsenate. The arsenic is a +5, and each oxygen is a -2. Now let's finish this one. 3 times -2 is -6. Once again, equal -3. And here we get +3 plus -6 is -3. Divide by 1 coming down, +3. Okay, in the Fallon aquifer, this is called arsenic 5. They're naming it according to its oxidation state. Whoops, that's a 4, huh? There we go. This one does not cause cancer. Okay. This one's arsenic 3. This one, at high doses, does cause cancer. Okay. And they haven't done the low dose study on this one, but at high doses doesn't cause cancer. And I helped speciate that with a Colorado environmental firm. One of the engineers came to Fallon, and I helped go out and get well water from the base and from different wells in Fallon. And we speciated all the arsenic from the aquifer, and it was all arsenic 5. Okay. And this is the one like in Taiwan or Bangladesh. They have other forms of arsenic that do cause cancer at high levels. And so now they're trying to get arsenic out of water throughout the nation. There's a belt, and we're right in the middle of the belt that goes all the way up to Canada. And we built the water treatment plant here in Fallon. Okay. And now Fallon water has no arsenic. Some of the wells do still because they're not on the city water. Okay. So we do this method to find out the oxidation number on the different atoms. Okay. Okay, let's do another one. Let's go Cr2O7 2 negative. This is dichromate ion. So that's how we set it up. And this is -2 oxygen. 7 times -2 is -14. So this has to be a +12. Let's see. Because +12 and -14 is -2. Oh, 12 divided by 2 is a +6. So the oxidation number on each chromium here is a +6. And here the oxidation number on each oxygen is a -2. See? So we had to go up and across and down to figure out the oxidation number on chromium. Because a lot of the transition metals, the oxidation numbers can change depending on which compound they're in. Okay. Keep doing examples. That's how we learn. Let's do a simple one. Okay, here's calcium phosphate. So that looks pretty complex, and we have to give the oxidation number on calcium, phosphorus, and oxygen. Well, if you have a neutral salt, split it up into ions, one of each. We don't care if there's 3 of these and 2 of these. Just identify the ions like we did metathesis. So here we have a calcium ion and a phosphate ion. Those are the ions. Once you identify what the ions really are, see the 2 came here and the 3 came here, you don't even worry about the formula, and do them individually. This is a +2 because monatomic ion, and then this we use a stairs in the attic, summed to -3. And here we get a -2, 4 times -2 is -8. And then we say, oh, what plus -8 gives -3 plus 5. 5 divided by 1 plus 5. So now in our original compound, we know this is a +2 calcium, this is a +5 phosphorus, and each one of these are -2 oxygens. So this is the easiest way if you have a neutral salt. Pull apart into 1 ion of each, and then usually get a monatomic ion somewhere, and then if it's polyatomic, you'll have to use the attic. Okay? So, let's do OF2. Here's a case where oxygen is not the known, because the rule states fluorine is always a -1. Always. So if oxygen's bounded to a fluorine, can't be a negative anymore. It's going to be a positive. And this is a molecule because it adds to 0. So this will be a -2 total, 2 times -1. Oh, and this has to be a +2. See that? A +2. And then you bring it down to +2 divided by 2 divided by 1. Oh, now we get a +2 oxygen. The only time oxygen's positive when it's bound to fluorine. Okay, any other time it's a negative. When oxygen's bound to fluorine, you won't know that till chapter 8 because fluorine likes electrons better than oxygen. Okay. Let's do ClO3 negative. And then ClO4 negative. So here we have chlorate and perchlorate. Okay. And once again, oxygen is not bound to fluorine, so they're -2s. 3 times -2 is -6. So here you need a +5, so it adds with -6 to get -1, and we bring it down because it's a 1 plus 5. So in chlorate, chlorine's a +5. Now let's see in perchlorate. 4 times -2 is -8. This is a +7, because +7, -8 is -1. Oh, this is a 1, so 7 divided by 1 is +7. Oh, so in perchlorate, it's a +7 chlorine. Okay? So now we're pretty good at oxidation numbers. Now let's do a practice exercise in the book. Show them why they're important. Or watch. I'll make one up. Okay, let's do a biology question. Let's take glucose and react it with oxygen, and we get carbon dioxide plus water. And so we have to balance it. There's a balanced equation. This is how we get energy in the body. We break down glucose, and not only do we breathe out the carbon dioxide and make some water, but we get a whole bunch of energy. Remember, in the body, I told you when we make energy, they're redox reactions. So number one, we're going to prove this is a redox reaction. And then once we prove that with the oxidation numbers, we're going to say which atom's being oxidized and which atom's being reduced in this redox reaction. Okay, so we already did this one. I'll let you look at your notes. So there's the oxidation number on the carbon, hydrogen, and each carbon, each hydrogen, each oxygen. 0, +1, -2. We already did that one. Oh, and this is elemental form, so that's a 0. I circle it. That's a 0. Oh, carbon dioxide. We're going to use the stair step. It's neutral. This is a -2 oxygen, -4. Oh, +4. So in CO2, the carbon's a +4. And the oxygen's a -2. And now in water, we don't even have to use any hydrogen not in a hydride or H2 by itself. Elemental form is a +1. And this oxygen is just a regular oxygen, -2. So that's the first thing I have to do in a balanced chemical equation. I got to write the oxidation number using the rules on every atom. And now I see what you do now. You look at atoms as they go from reactant to products and see if their oxidation number changes. Oh, here's one that changes. Carbon is going from a 0 to a +4. So you look at the number line. Here we have 0, 1, 2, 3, 4, and these are pluses. These are oxidation numbers. Then we have -1, -2, -3, etc. And so carbon started as a 0 in the reactants, and then it went to a +4. So when an atom gets more positive, it's losing electrons, it's oxidized. So if you plot the oxidation numbers on the atom as they go from reactant to product, and the line goes to the right, getting more positive, that atom's becoming oxidized. So this is an oxidized atom. It's losing electrons. Okay, the hydrogen's a +1, +1. It hasn't changed. What's the other atom that changes? The oxygen, right? This one's not changing, but this one's going from a 0 to -2. And so the oxygen is changing. So we go ahead and put a line here from here to here. And here we're going from a 0 to a -2 on each oxygen atom in that process. So now I plot those. I started out as a 0, and I ended up as a -2. And so therefore my line's getting more negative, so this is reduction. When an atom is getting more negative, even if it's going from like a +3 to a 0, it's still going to the left, getting more negative. That'd be reduction. And so this is our reduction half reaction, or reduced. So we do have a redox reaction, yes. And the answer is the carbon is getting oxidized, and the oxygens and the O2 is getting reduced. See that? And so you should be able to do that. And there's a practice exercise in your book. like practice exercise 4.9. 4.9. Where they show an example on page 134 where you identify what's being oxidized or reduced in a redox reaction. So you should be able to do a problem like this, okay? And to do it, you have to start and put the oxidation number on every atom, and then you find out which atoms are changing from reactant to product, and if they're losing electrons or getting more positive charge on the number line to the right, that's the oxidized atom. And then if they're getting more negative to the left, that's a reduced atom. And once again, I forgot to mention, these always occur together. You can never have separate oxidation and reduction because electrons don't flow in space. Something has to touch them to exchange electrons, okay? And so these are yin-yang, they occur together always. And so if we have oxidation, we're gonna have reduction somewhere in our reaction. And by using oxidation numbers, we can find out which atoms are participating in the redox, okay? Now we can learn the reaction. Now we've got the background with oxidation reduction, and we're going to do our last topic of this lecture and learn how to do a single displacement reaction. A plus BC goes to B plus AC. So here we've got a neutral compound, and here we have a cation and anion. And now the cation's going to become neutral, and the neutral species is going to become a cation. And so that's a single displacement. A is displacing B out of the salt, and then it's going into the salt, and then B is coming out. B is getting reduced, gaining electrons, and A is getting oxidized. This one's getting oxidized, and B is going to get reduced. Okay. It's called single displacement. Reaction. Okay. And so you're going to have to do these type of reactions using this activity series. So let me put this one up for you. And this is in your book, and this will be given on an exam or quiz on page 136. Page 136. And here it is. Ta-da. You can tell I'm getting a little tired, just like you, huh? This is called an activity series. And you'll notice these are all metals except for not one non-metal, hydrogen, and then all metals. And so the neutral, these are called half reactions. These are written as loss of electrons, barium plus barium 2 plus 2 electrons. So these are all oxidation reactions because they're all losing electrons. And these are called half reactions. And we can flip any one and make it a reduction. We can go like lithium ion plus 1 electron goes to lithium metal, neutral metal. So what I did, this is an oxidation of lithium metal to its cation and electron, so I can flip it, and now it's a reduction half reaction. Reduction half reaction. Oxidation half reactions. So any one of these can be flipped. And you put two half reactions together, you got a redox reaction. Okay? And so to get a redox reaction in this series, which we're going to do, we're going to take one oxidation reaction and add it to a flipped reaction, a reduction, and add them together to get our total redox reaction. Okay? So let me show you how to do that. Let's take lithium, oxidation reaction, okay, And we can add it to any reaction below it by flipping it and add them together. The only way this series will give you a redox reaction, this is really important, put it in your notes. The one on top has to be non-flipped. Oxidation half reaction. And then wherever we take that one, we can take any half reaction below it and flip it to make it the reduction and add them together, we get a redox. But if you take one as the oxidation reaction, you cannot use one above it for a reduction. You can't flip it. It won't work. It'll be no reaction. They'll already be happy, because what this series means, ease of oxidation. This is an activity series. It's saying this reaction likes to lose electrons more than any reaction below it. Okay? So let's take manganese. Manganese will react with any one of these below it if you flip it, because manganese likes to lose electrons better than any of these half reactions. So to be energetically favorable, he says, you flip and I'll take my electrons here that I make, then we can have a reaction. But manganese will not flip a top one, because a top one likes to lose electrons more than manganese. And so manganese is going to have to flip if you get a half reaction above it. So you've got two things to consider. We're going to give you two half reactions. Number one, you've got to say, is there a reaction? And if there is a reaction, you've got to complete it and balance it. Okay? And I'm going to show you a logical way, then I'll show you the book way. Okay? This is just to give you greater understanding. If you don't understand it, don't worry about it, but some of you it will help. And so, because you don't get full knowledge of redox reactions until chapter 20 in electrochemistry, and so you're not going to have total understanding of redox reactions this time. So it's a little gimmick and a little bit of understanding to be able to do these single displacement reactions and balance them. So what I just told you now, lithium will react with any half reaction if we flip it. So let's take chromium here, and let's flip it. So we're going to put the neutral over here, and then it's chromium 3 plus aqueous plus 3 electrons. So there, I'm going to add two reactions. I take the top one unflipped, the one below it flipped, and then I'm telling you there'll be a redox reaction. So now you just add them together. But now before we add them, we have to use a multiplier sometimes, because electrons lost has to be electrons gained. And see, the oxidation reaction is losing electrons on the right, a product, and the reduction half reaction is gaining electrons on the left. Okay? So here, we're going to have to multiply the lithium equation by 3, because then we'll have 3, we're going to multiply each term by 3. We can do that algebraically. And then we'll have 3 electrons lost equal 3 electrons gained, because we have to cross out the electrons and not show them to have a balanced redox. So now we're going to add 3 lithium solid goes to 3 lithium plus 3 electrons, and then chromium 3 plus 3 electrons goes to chromium solid. So now here's the two half reactions we're going to add, where we have electrons lost equal electrons gained. So we subtract 3 electrons from both sides, and then nothing else cancels, so we bring it down. So here we get 3 lithium solid plus chromium 3 plus goes to 3 lithium plus chromium solid. And I guess we can put aqueous there, aqueous. So there's our balanced redox reaction by adding two half reactions from the activity series. See? And this will work every time. Okay? But the author is not showing you this part, but I'm showing it for conceptual reasons right now. And I'll show you how to do it his way, but this will work every time. And this is called the net ionic redox reaction. Because this is really came from a salt, but they're saying the anion from the salt is a spectator. It crosses out, just like it's going to be a spectator. So doing this method I'm showing you here is going to give you the net ionic equation. And in this class, chapter 4, I don't care if you give me the net ionic or the total molecular balanced for this one. Either one. If you can recognize the redox and balance it, I'm happy. Okay. The author wants you to give the net ionic one. Oh well. On my exams and quizzes, you can give me either one. If you do it this way, you'll always get the net ionic. If you do it the book way, I'm going to stop at the balanced molecular instead of pull apart and cancel. Okay. Let me show you another one. I'm going to take H2 gas, and there's this reaction. Goes with 2H plus 2 electrons. So here's a neutral form of hydrogen on this series. And now to get a reaction, I can flip any one below it. So I'll take silver. And I know I'm going to have a reaction because I taught you that logic. But once again, I have to balance my electrons, so I have to multiply this one by 2. So 2 times this is 2, 2 times this is 2, and 2 times this is 2. Multiply each term by 2. You can do that in algebra. And now the electrons cancel. And now I say 2 silver ions plus H2 gas yields 2H plus 2 silver plus. Oh, made an error there. There's no plus there. That's a solid. And so there I have a balanced net reaction, ionic reaction consisting of these oxidation redox reaction, and it's balanced. So this is saying if you have a silver salt and you bubble hydrogen gas in there, it's going to turn it's going to take the electrons from the H2, and silver will come out of solution as pure silver, and you'll have acidic protons floating around in the solution. Okay. Let's do another one with hydrogen. Let's take aluminum. So here we have aluminum oxidation reaction, and we're going to react it with hydrogen. But since it's below it, it's got to be the reduction one, so we're going to flip it. See that? We flip this one because it's got to be the reduction one, because this one likes to lose electrons more because it's higher up. And now, oh, here we're going to have to multiply each one of these by 3 and each one of these by 2. So we get 6 electrons lost and 6 electrons gained. Because 2 and 3 are the lowest common multiple, whatever it's called. You want the lowest common multiple of the electron numbers. And so we're going to add 2 aluminums to get 2 aluminum 3 plus 6 electrons. We're going to add that to 6 H pluses plus 6 electrons, going to 6 H2s. And now we can cancel the electrons, so we can add these 2 half reactions. So 2 aluminums plus 6 H plus gives 2 aluminum 3 plus 6 H2 gas. And this is the definition of an active metal. This is important for you to know. Any metal above hydrogen in this series is called an active metal. Okay, it's called an active metal. Okay. And it's called an active metal. The definition of an active metal is a metal that you put in acid, it will dissolve the metal to produce the cation and then evolve hydrogen gas. So once again, that's a definition of an active metal. You put the active metal in some acid, it will dissolve the metal, form the cation, and then generate hydrogen gas that will bubble up. Where the ones below hydrogen are called noble metals. Noble metals will not react with an acid to give hydrogen gas in the cation. Noble means unreactive. Noble means they like to keep their electrons. And that's why the jewelry metals are noble. See, these are all jewelry metals, are very stable. So you can find gold from 2,000 years in the dirt and it's still pretty lustrous gold instead of oxidized gold, okay, in the crumbly salt form. Okay. So now, let me do a reaction like the author would do it. In the next film, next lecture, I do a lot of these. But let's say I was doing one of these on it. This is how they'll appear on the test or a quiz. Let's say I take zinc solid plus nickel chloride. Okay. They're going to say, is there a redox reaction? And if so, complete and balance the reaction. You don't have to give me the net ionic. And here they're giving you the anion, even though you don't have to have it. It could just be nickel 2+ for net ionic. But they're going to give you the salt. And so you look at zinc, you go, oh, here's my zinc half reaction. And zinc, since it's on the left, it's a reactant, so this has to be the oxidation reaction if this is going to go, because my zinc solid's on the left, and this is on the left of the arrow. So I look where nickel is. Oh, and here's nickel, and sure enough, nickel's in the the 2+ form. It's the cation, right? It's the cation form of nickel as a reactant. So sure enough, here we flipped this one, didn't we? We flipped it. We made nickel on the left, and then our product's going to have nickel solid on the right. So we do have a reaction. Okay, we do have a reaction. So now we just have to complete it. So the zinc's going to go in the salt because we got Zn losing the electron. See, now it's 2+. See, it's 2+ over here. And it's going to react with 2 chlorides to give a neutral formula. Plus, nickel's going to come out of solution, solid. See, because we flipped this. So nickel's going to go over there. The Ni2 is going to be over here. And they're both 2, 2. So it's 1, 1, 1, 1 balanced. It's already balanced. 2 chlorides, 1 nickel, 1 zinc, 1 zinc. And now we have a balanced redox reaction. You don't see the electrons because it's balanced, but that's a balanced redox reaction. Okay? If we would have had this, here, we find zinc again, and it's the oxidized form because we start with zinc neutral. Oh, and then the lithium form, we flip that one. Oh, but that doesn't happen. We put no reaction. Because lithium likes to lose electrons more than zinc, and here it's already lost the electrons. And zinc likes to gain electrons more than lithium because it's below it, and it's already gained, so they're already low energy. So they don't want to exchange electrons. They're in their low energy forms, according to this activity series when you compare the two. And so there's a no reaction. So remember, to get a reaction, you look at the reactants, the cation has to be below the neutral species. In other words, the cation reaction has to flip to become on the reactant side to start the reaction. Okay? So now we're done with this lecture. And the neat thing is you can stop and take notes and listen whenever you want. This will be on YouTube, and I'll give you the URL once I put it on YouTube. And I'll give you the URL for the next lectures too if you want to get ahead. But this is the lecture to stay ahead that replaces next week's lecture on Monday because I'll be in the hospital. Okay, good luck with Chapter 4.